Hello everyone, welcome to Rasayan Academy, and today's video is about IR spectroscopy. Right, it's about IR spectroscopy, and today it is definitely on structure determination. Alright, and this is the fourth video in the same series. So I'm just writing 4 over here. It's the fourth video in the same series. So today guys, we are going to talk about the structure determination of alcohols and phenols and ethers. Alright, so let's begin with it. And before starting our class for today, let me just introduce myself. So my name is Jagriti Sharma and I am an educator on the Unacademy Plus platform, where we are conducting live classes and helping students to prepare for the CSIR UGC NET exam. Also we are so basically guys, I just want to introduce you to the types of classes. Basically we are having 3 types of classes. One is the special class, which are 1 hour live classes basically. So these are 1 hour live sessions, and if you are able to attend them, if you follow me, then you will get regular updates and you will be able to attend the live class. And if you are not able to attend the live class, you can see the recorded sessions. Okay, all of the sessions are recorded and they'll show you in simple color like this, yellow colors. So basically they are, all of them are our my live classes. So what you can do is you can just click on one of them and you will be able to see what we have been talking about for 1 hour in the live class and the special classes. And there are a lot of such live classes, and my focus has been always to solve more and more practice questions as well as previous year questions in the live class, so that they are available to you. And guys, these are free classes, live ones, right? And then we have free video courses. So these video courses are just like the video that I am making right now. So these are small video courses, right? 15 to 20 minutes, and they're also very knowledgeable and very helpful for your preparation. I've also put in a lot of previous year questions in them, so you can just go on the Unacademy and watch some of the free courses as well. And guys, what is a plus course basically? So in a plus course, if you visit the Unacademy website right now, you will be able to see 2 of my plus courses for the month of January 2020. Basically, I'm having a batch course along with 2 other educators, and I am teaching organic chemistry over there. Alright, so that is my batch course for January 2020, and my individual course in the Plus platform is organic reaction intermediates. Okay, so it is organic reactive intermediates or reaction intermediates, right? And in that course, I'm definitely covering the carbenes, nitrines, carbocations, benzyne, carboanions, radicals, and so on in detail, definitely. So the Plus platform is a paid platform, okay? And definitely guys, if you like my courses, if you like the content, then I would suggest you to come up on the Plus platform, because guys, we are this is the month of December 19, and right now we are studying we are focusing on the strategy, how to prepare the exam for the next 6 months, right? And after that we are just going to go on to the content. We are just going to start with the content, right? And if you want to subscribe, then there are various courses. We are 1 month course, a 3 month course, a 6 month course, 12 month, as well as 24 month course, right? So if you want to subscribe, then you can use my code. This is a referral code and it is going to give you a 10% discount, right? So my code is Jagriti S, and it is going to give you a 10% discount on whichever the subscription package you want to have. And guys, you are going to get more information on how to use Unacademy, how to explore Unacademy, right, on 19th of December on YouTube, because I will be live on YouTube and I am going to discuss about how to explore Unacademy to its best, how to extract knowledge from the Unacademy to its maximum, right? So it is going to be on the Unacademy CSIR channel, right? Unacademy CSIR channel. Alright, very simple name. I hope you'll be able to remember it. Alright guys, so now let's start with our class for today. So today we are going to talk about the IR spectra of alcohols and phenols. Right, so what are the characteristic peaks that we are getting? We are going to see that first, okay? Alright, so the characteristics peak are definitely the OH stretching, right? So guys, this is our hydroxy group basically. So see, we focus on the functional groups while we are checking for the IR spectra, right? So IR spectra is all about functional groups. So what is the major functional group in alcohol and phenol? Definitely is our hydroxy group, isn't it? So the hydroxy group OH stretching is definitely going to take place between 3650 to 3300 centimeter inverse. This is our normal range. Alright. What about the characteristics? Right. So these are the characteristics. The free hydroxy OH bond gives a sharp peak between 3650 to 3600 centimeter inverse. We are talking about free OH bond. However, the hydrogen bonded OH bond gives broad peak between 3500 to 3300 centimeter inverse. So what just happened? What did you just notice? First of all, we are changing from a sharp peak to a broad peak. Secondly, the frequency has also decreased, right? So the frequency of the OH bond has also decreased on hydrogen bonding, right? Hydrogen bonding. And guys, I hope that you remember the conjugation effect on the frequencies of alkenes, right? So the hydrogen bonding is having a similar effect of just like the conjugation was having on the uh, alkene system. So here also the value is decreasing. The frequency or the wave number value for the OH bond is decreasing because of the hydrogen bonding, right? And guys, the hydrogen bonding is of two types. It is intramolecular, right? It is intramolecular and intermolecular. Okay, and I can't tell you this very easy questions come into the CSIR exam which are directly onto this concept, right? And yeah, so in the December 2019 examination as well, we had a question that a molecule is showing some peak. Let's say I'm giving you some molecule. I don't remember the compound exactly, right? But definitely there was a question. The exam was very recently, it had happened, and I'm not even having the question paper basically. Anyways, so the question was very simple, that I'm having a compound, right? So the question is asking that on dilution, basically we are having a alcohol or a phenol, right? So definitely it is going to show a hydrogen bonding, yes. But on dilution, the hydrogen bonding decreases and the frequency of the OH group again increases, right? So which type of bonding is that? Is it intramolecular hydrogen bonding or is it intermolecular hydrogen bonding? That we have to determine. So guys, on dilution only one type of hydrogen bonding can decrease, and which is that intermolecular hydrogen bonding, because on dilution these molecules are going to go very they are going to go apart from each other, and that is why we can say the interaction between one of the hydrogens of one hydroxy group and the other oxygen, which can come from the OH also, it can come from the nitro also. Okay, so the interaction between two molecules decreases, and that is why on dilution the intermolecular hydrogen bonding also decreases. Okay, right. So there was a CSIR question on this concept, and why is that not going to happen in the case of intramolecular hydrogen bonding, guys? Why is that not going to happen in the case of intramolecular? Because it does not care about dilution, because there is hydrogen, there is a acidic hydrogen right over here in the molecule, and there is a oxygen which is forming the hydrogen bond, and it is intramolecular. So definitely it is already isolated, the whole molecule is already isolated from similar another molecule. So the intramolecular hydrogen bonding is not going to be affected by the dilution, right? So it's a very simple question, and it has been asked a lot of times. So I hope that you are now clear with how important hydrogen bonding is and how easy it is as well. Alright, so I'm just making some space. We are going to focus on the values again. So this was just a conceptual question, and we will be solving a lot of such questions, guys, in the in our upcoming classes basically. Okay, so now we are also going to talk about carbon oxygen stretching, which is between 1260 to 1000 centimeter inverse. Alright, so this is our CO stretching, right? We are talking about stretching frequency. Okay, So this provides information about alcohol structure. What is the type of stretching? This provides information about the alcohol. Let's say we have taken an example of 2-butanol system, right? We have taken 2-butanol over here. So in this molecule of 2-butanol, what are the peaks that we can observe? Guys, first of all, in the last few videos, we have talked about that we are going to focus on the left part of the spectrum because it is easier to interpret. Alright, we are just going to focus on the left part, right? So definitely we are, as we can see over here, it's a very broad peak, isn't it? This is our very broad peak, and it is showing at around greater than 3400, right? It is around 3400, or let's say greater than 3400. Definitely it is our if we are already having an alcohol, definitely it is our OH stretching, and it is broad because the molecule is hydrogen bonded. Just now we studied if it is dilute, or let's say not hydrogen bonded, then it is going to be a very sharp peak, but here it is hydrogen bonded, so a broad peak. Okay, right. So what else do we observe? We observe CH stretches, and this is sp3CH stretching, which is on the left hand side of the 3000. Let's say this is our 3000 basically. So if this is 3200, this is 2800, then this is going to be 3000, right? So if it is on the right side of the 3000, definitely it is lesser than 3000, right? It is going to be around 2900 centimeter inverse, right? So for the sp3 carbon hydrogen bond, we had discussed it is going to be on the right side. For the sp2 hydrogen, it is going to be on the left side of 3000 centimeter inverse. Okay, it's an easy way to remember stuff, right? Okay, what else we see? Now we are going to jump into the fingerprint region, and guys, definitely we are going to observe the bending vibrations. CH2 bending at 1475, or let's say 1500. CH3 bending is going to be around 30-50 centimeter inverse. Okay, also we can see one more very important band, which we can see over here in this region, right? In this region around 1100-1150. Okay, so this is our carbon oxygen stretching frequency, and over here, as we can see, we are getting multiple bonds. We are getting multiple bands. Sorry, we are getting multiple bands over here. All right. Okay, guys. So this is what we are having in the IR spectrum of 2-butanol basically. All right. Okay. So now we are going to move forward. And we are going to consider the structure determination of paracresol basically. So guys, we know what is the structure of paracresol, right? This is our OH and this is our CH3 right over here. So when we are talking about paracresol, definitely there is OH group, so there will be oxygen hydrogen stretching, which is going to be hydrogen bonded, right? Then we are also having sorry, we are also having CH3 bending and stretching vibration. There would be aromatic carbon-carbon double bond stretching vibrations as well as bending vibrations. Okay, so in the aromatic region there is going to be a lot of bands, right? So let's now jump on to the spectrum. So on the left hand side of the spectrum, what do we see? Okay, we see a very broad peak, and definitely it is characteristic to our oxygen hydrogen stretching, and it is hydrogen bonded. Okay, also we can see, alright guys, so we can see very weak peak over here in this region, and as I can see, this is our CH stretching, and it is a combined peak basically. For the peaks which are having a value greater than 3000, it is going to be our sp2 carbon hydrogen stretching, and for the values which are less than 3000 centimeter inverse, it is going to be around it's going to be for the sp3 carbon hydrogen stretching. What else can we observe? Guys, look very closely. We talked about para substitution, isn't it? We talked about para substitution. So if you are getting one peak which is greater than 800, or let's say around 800, one peak around 800, it is para. One peak which is less than 800 or which is around 750, that was ortho substitution. Also, if we look at the overtones, it is going to be a simple peak over here like this. Okay, shouldered peak basically. So this is going to confirm that we are having para substitution, right? And now going to the aromatic region, definitely we are going to see around 1600. Yes, so around 15 to 1600 we are having our carbon-carbon double bond, and it is going to give us multiple bands because there are 3 carbon-carbon double bonds. What about carbon-oxygen stretching? So again guys, for the carbon-oxygen stretching frequency, so this is the area around 1200 centimeter inverse, 11 to 1200, and guys it is again giving us multiple peaks. So we can say the carbon oxygen stretching is always gives us broad peaks and multiple peaks. Alright, so we have seen that in the two spectrum over here, and I would suggest you to go and see more in the reference book. Alright, so this was all about the spectrum of para-cresol. We identified the hydrogen bonding OH group, we identified the para substitution, we identified the aromatic bonds over here, carbon oxygen stretching, also the para out of plane bending vibration as well. Okay, this is the fingerprint region, this is the values for the bending vibrations. Alright guys, so now we are going to move forward, and now we are going to look at the carbon oxygen stretching frequency, that what are the or what can be the different values for different alcohols, right? So as I have written over here, I've just generalized it over here, and I have written that the the carbon oxygen stretching frequency for phenol is greater than 3 degree carbon is greater than 3 degree alcohol, then 2 degree alcohol, then 1 degree alcohol. So here we are talking about the carbon oxygen stretching frequency. Okay, similarly if we consider the oxygen hydrogen stretching frequency, what is the order? It is just opposite. So for phenol it is going to be less than 3 degree alcohol, which is going to be less than 2 degree alcohol, which is going to be less than 1 degree alcohol. So the order is directly opposite. So if we are talking about, let's say we are first of all we are talking about phenol over here. Okay, so in this molecule of phenol we can see the OH, or let's say the carbon oxygen first of all. So we are talking about carbon oxygen stretching frequencies over here. So it is 1237 centimeter inverse, going on to 3 degree it is 1159, then 2 degree 1113, then 1 degree 1069 centimeter inverse. So it is decreasing with the in this order basically. Alright, and if you are considering the OH stretching frequency, it is increasing slightly, 3614 centimeter inverse, 3618, 3628, 3636. So it is, even though it's a very small change, but definitely it is increasing, right? So this order is just the opposite, it is just the opposite, right? And why does this happen? Why does this happen guys? That why is the value for phenol, why is the frequency value of OH stretching, it is least for phenol, right? So we can explain this on the basis of resonance. How? Because if we are drawing resonance structures, then the oxygen lone pair is taking part into resonance into benzene, and it is going to, even if the hydrogen is lost, it is going to give us a very stable phenolate ion, right? So because of that, the oxygen hydrogen bond becomes very weak in the case of phenol. That is why phenol is having the least value. And as we go on as we go on getting into primary alcohol, there is no resonance, as well as there is no plus I effect as well. So here also there is plus I effect of the carbon, right, of the methyl group, and definitely for primary hydroxy group we are not having any such effects, and the interaction of oxygen with carbon is the least, and that is why for the primary carbon, the primary OH group is having the maximum stretching frequency value. Alright, I hope that this concept was clear to you guys. Now we are moving on to the IR spectrum of ether. Okay, so what do we see? What can we see in the IR spectrum of ether? Definitely there will be no hydrogen and oxygen stretching frequency. There will only be carbon oxygen stretching frequency, right? It can be COC stretching, it can be COC bending as well. So we are going to see both the stretching and bending vibrations. So let's say we have taken an ether over here like this, right? So it's a very simple ether, isopropyl ether it is, and at around, definitely guys, this is what we are going to see, because there is going to be carbon hydrogen stretching, and we see the value at 3000 centimeter inverse. Alright, Similarly, we observe our CH2 and CH3 bands and the same value 1475, 1500 or 1350, right? CH3 bending. Okay, what else do we see? I only see a carbon oxygen stretching frequency, and the rest of the area is also very neat and clean. Basically, we are not having much bands for the ethers, right? So the most prominent is the carbon oxygen stretching frequency, which is around 1300 to 1000 centimeter inverse. And as we can see, it's a very sharp peak. It's not a weak or medium peak, it is a sharp peak, okay, at this value 1300 to 1000 centimeter inverse. Okay, only carbon oxygen stretching and no oxygen hydrogen stretching or carbon oxygen double bond stretching, this confirms our ether. So we might think that the data for the ether is very less. We might think that, but guys, when there is a oxygen, let's say we are having a molecular formula like this, C2H6O, and you have to determine the structure. So basically, if you are not having a carbonyl frequency which is around 1700, if you are not having that peak, no carbonyl. If you are not having a broad peak over here, then also there is no OH group. Alright, so definitely if we are not having all these things, then definitely for one oxygen it has to be ether, isn't it? It has to be ether, right? And we can confirm that by the CH3 bending and stretching vibrations and so on. Alright, so I hope that this was clear to you. Now we are going to discuss further more spectra, and right now we are on to the spectrum of amines. Alright, so guys, what do we see in the IR spectra of amine? What are the characteristic stretching and bending vibrations? Let's see quickly. So the NH stretching occurs between 3500 to 3300 centimeter inverse. This is our nitrogen hydrogen stretching frequency. And guys, don't forget, if you are having primary amines, then the primary amines are going to show you symmetric as well as antisymmetric stretching, and definitely the antisymmetric or asymmetric stretch is going to have a greater value, frequency value, alright, as compared to the symmetric stretch. Okay, so definitely guys, the 1 degree amine is going to show 2 bands, the 2 degree amine is going to show only 1 band because there is only one nitrogen hydrogen bond, and 3 degree amine is going to show no nitrogen hydrogen stretching frequency. So there will not be any peak at this value, no peak at this value, 3500 to 3300 centimeter inverse. Alright, so let's also consider the NH bending vibrations, and after that we are going to see some real spectrum. Okay, so the NH bending vibration is between 1640 to 1550 centimeter inverse. Alright, so even if you don't remember the exact value, you are just going to take an average of this and try to remember the average value, 1550 centimeter inverse for our amines. Okay, NH bending vibration basically. Okay, so for 1 degree amines it is going to be a higher value, for 2 degree amines a lesser value, and for 3 degree amines we are not having nitrogen hydrogen, so no value. Okay, also we are going to see carbon nitrogen stretching between this value 1350 to 1000 centimeter inverse. And let me tell you one more thing guys, that the bending vibrations of amines are not always reliable information, right? Because there are so many peaks in this region for our normal any molecule, let's say ether, right? So for any molecule, and even if we are having some aromatic system, then the carbon-carbon double bond peaks are also in the same region. So basically it becomes very tough to interpret the molecule. So we can say that these values don't come very handy in interpretation, right? They're not very useful, but still we can just try and understand what are the possible values. All right, so now we are going to see some real spectrum. Okay, so let's talk about the IR spectrum of cyclohexyl amine. Alright, so if we are talking about the IR spectrum of cyclohexyl amine, so first of all, if you see the structure, it is a 1 degree amine guys. So if it is a 1 degree amine, we must expect that there must be 2 nitrogen hydrogen stretching frequency, right? One should be symmetric, one should be anti-symmetric stretch. And guys, we always should remember the antisymmetric stretch is going to be greater in frequency than the symmetric stretch. So guys, this is how it is going to appear. Looks like a doublet, but it is not a doublet because the frequencies are so close. That is why it is looking like a doublet. Okay, so this one is for this anti-symmetric, it is on the left hand side higher value, this one is for the symmetric. All right, so this is our two nitrogen hydrogen stretching frequencies, and it is going to be around 3500 centimeter inverse. All right, okay, now moving forward, definitely we are going to see, as we can see over here guys, this is 3000 and we see our peaks on the right hand side, which means it is less than 3000. Definitely it is going to be for sp3 carbon hydrogen stretching. Okay, what else do we see? We also see a medium peak. This is a medium peak over here, and this is on the range, this is our 1600 range, right? Roughly 1600 or 1650. Okay, so at this range I can see a peak, it is medium strength, and it is our nitrogen and hydrogen bending vibrations. Okay, similarly I can see a very sharp peak over here in the same region at less than 1500 basically, or around 1500. This is our carbon nitrogen stretching frequency. Okay, so basically guys, it was a very simple molecule over here, right? So there are no aromatic double bonds to interfere in this 1600 region. So now we are getting very clear very clear peak over here in this region 1500 to 1600. All right, so I hope the spectrum was clear to all of you. Now we are going to move forward to another such spectrum. Now guys, we are going to talk about our N-methyl aniline. So this is our 2-degree amine first of all, and secondly it is having aromatic system, isn't it? It's having the aromatic system like this. All right, and definitely we are going to see what are all the peaks that we can get. So first of all, we are going to get a nitrogen hydrogen stretching frequency, and because it is a 2-degree amine, we are just going to get one peak. And look over here guys, this is greater than a medium peak, right? It is greater than a medium peak, it is between a strong to medium, right? And we are getting our nitrogen hydrogen stretching, such a sharp peak that we are getting over here, and definitely it is having a greater value. Okay, similarly at around lesser than, also we are having a mix of values, because the carbon hydrogen stretching is also for the sp2 carbon and hydrogen, and it is also there for the sp3 carbon and hydrogen. So that is why we are getting such a mix, not single peak. There are a lot of peaks over here which are interfering with each other basically. Then what else do we see? What else do we see over here? Let me just make some space. All right, so what else do we see over here? First of all is at this area 1600, right? 1500 to 1600, what do we see? We see two sharp peaks, right? We see two sharp peaks, and guys, one of them has to be our carbon stretching frequency, and one of them is also the NH bending. So guys, we cannot very easily interpret the NH bending vibration when the aromatic system comes into play. Okay, similarly here in this area of around 12 to 1300, this has to be carbon nitrogen stretching frequency. Okay, so we can just assume that these are the peaks over here, and also we can calculate, because we can we just know this formula, that our frequency is inversely proportional to the reduced mass. So we can also calculate the frequency, and then we can be sure ki okay, this value is there for the carbon nitrogen band. Okay, all right, what about the substitution at benzene? For benzene over here we can see only one carbon substitution. So for mono substitution, yes, for mono substitution we had two signals, two peaks of almost equal intensity, and they're also strong peaks, right? And for so these peaks come into the bending vibrations basically, and these peaks are around 720 to 750 centimeter inverse. Similarly in the overtone region, so these are the overtones, right? So in the overtone region we can see this type of pattern, and if we remember, it was for mono substitution. Alright, so we just have to see little hints about the system, right? So first of all, we saw it is a 2-degree amine. Why? Because we are only getting one peak for nitrogen hydrogen. Okay, secondly, we saw that in this region, in this 15 to 1600 region, we are also having aromatic carbon-carbon double bond stretching frequency, as well as the bending vibration, NH bending. Also we saw carbon nitrogen stretching. Also we saw the mono substitution, out of plane bending vibrations, and in the overtone region we just confirmed it with the type of pattern that we see over here. You don't have to remember the pattern, right? But when you are doing the actual comparison for one spectra to the other, then definitely you can compare it with the literature value or data that we are having basically. All right. Okay, so guys, I hope that you are able to get some knowledge over here. I hope that you are understanding stuff. Alright, so now we are going to talk about IR spectrum of tributyl amine. So it is our tributyl amine, isn't it? So it is going to have, let's say I'm writing it like this, so it is our 3-degree amine, isn't it? So it is not going to have any nitrogen hydrogen stretching frequency, isn't it? So yeah, so this area is all blank. The area around 3500 to 3600, this is all blank over here. No nitrogen hydrogen stretching peak over here. Okay. Similarly, at around 3000, it is less than 3000, definitely we can see. So all of the hydrogens have to be sp3 carbon hydrogens, right? So all the CH stretching is definitely for the sp3 carbon hydrogen stretching. Okay. All right. Similarly, for CH2 bending, we are going to see it around 1475 to 1500. For CH3 bending, it is 1350. Alright. Now also we can see the carbon nitrogen stretching frequency, which is around the same region. Alright. 1100, 1150 to 1200 basically. Alright. So these are our major values in the IR spectrum of tributyl amine. No nitrogen hydrogen stretching. Similarly, a very simple carbon nitrogen stretching is only observed extra, because the CH stretching, CH2 bending, CH3 bending is all for the hydrocarbon chain basically. Alright. Okay, so I hope that this was understandable, right? Yeah. So I hope that this was understandable to you guys. I hope it was good, and I hope that you are able to take some knowledge at least from this course, from this video of mine. And if you liked it, then please like, share, as well as subscribe. And guys, definitely share to your friends, and I would request you to attend and to visit my page at the Unacademy, right? Because guys, definitely there is a lot of free content which is already visible. If you watch my special classes, you will be able to see a lot of previous year questions as well as practice questions. Okay, and do follow me on the Unacademy platform as well, because then you will be able to get regular updates on whatever classes I am posting. My classes are also I'm taking special classes on the Unacademy, plus classes on the Unacademy. Along with that, I am also taking live session on YouTube. Alright, so these live sessions on YouTube are definitely on the Unacademy CSIR channel, and I don't want you to miss anything guys, because I try to put in my best efforts for all the classes. So I would suggest you to follow me so that I can give you regular updates. And thank you so much for watching. I'll see you in the next video.